So, when we use a mechanism, there is an input or a set of inputs which are actuated and an output. Now, we need to relate these inputs to the output. There are various requirements. For example, if I ask, if I need this output, what should be my inputs? This is one kind of relation I seek. Or if I specify the inputs, what should be the or what will be the output? So, in today's lecture, we are going to look at these issues. This problem is known as the displacement analysis problem. We are going to define and look at problem of forward and inverse kinematics. So, displacement analysis has these two problems, forward kinematics and inverse kinematics, and we are going to restrict ourselves today to this 4R chains, forward kinematics of a 4R chain. So, displacement analysis, as I just now mentioned, that we would like to know the input output relation. We know that a mechanism transforms the actuator inputs to certain motion outputs. There can be multiple inputs, but usually there is one output. So, this input output relations is what is the subject matter of displacement analysis. So, inputs are the actuator displacements. For example, in case of a rotary motor, what is the angle by which the motor rotates? In case of a hydraulic actuator, it will be what will be the throw or extension of the hydraulic actuator. So, these are the inputs. The output would be in terms of the link displacement. So, output link displacement, this could be an angle, it could be position and orientation like in a robot, a combination therefore of linear and angular displacements. So, these are the outputs or output. Determination of this displacement input output relation is what we are going to study under displacement analysis. So, let us look at this example. So, here I have an example of a scissor that is used, or a clamp maybe, it is used for laparoscopic surgery. So, we have the surgeon's finger operating this handle can be considered to be fixed. So, when I change this angle, when the input link moves by this much angle from this configuration to this dashed configuration, how much is the output motion of the clamps? This is one kind. Here I have shown you the landing gear mechanism of an aircraft. If I expand this actuator, then as I have shown you, this rotates, this link rotates the ternary, and that folds the wheel or the wheel link. So, the question is, how much should this actuator expand so that the wheel gets completely folded? Now, in case of robots, remember robots are mechanisms with degrees of freedom 2 or more. Now, as soon as you have 2 or more degrees of freedom, you have that many actuators, and you can control the displacement of the output of the robot. So, for example, you can control the motion in x direction and the motion in y direction, let us say. So, 2 degrees of freedom. So, I can control these two. Now, successive, because these two are independently controllable. So, I can, if I want to go from this point to this point, I can choose to go like this, or I can choose to go like this, or I can choose to go in this manner. So, successive displacements of the output generates a path. Now, in case of robots, therefore, this displacement analysis is about finding the actuator inputs so that it can generate a certain path. So, what the path is of the output link or the end effector. Let us look at this example of an excavator. We know that this has got 2 degrees of freedom. We can ask the question, if I want to take this bin in this path, how should I actuate? How should I actuate the hydraulic actuator so that the bin travels in this path? So, the displacement analysis in the case of robots is a little more complicated, because it affords this freedom. I can choose my path, I can choose a different path, or when I am dumping I might choose another path. So, the question is, what should be the input actuation? Same case for this robot, Puma robot. If I want to have this end effector move in a certain path, how I should move the angles of these motors so that the end effector moves along this path. Now, there are two problems in displacement analysis, as I was mentioning. The first problem is, given the input, that means given the actuator motion, it could be angle, it could be throw of the hydraulic actuator, given this input, what will be the output? So, for example, if I say that this angle should be say 0 degree and this should be 90 degree, where is my hand? This is called the forward kinematics problem or the direct kinematics problem. So, let us see this. So, forward kinematics problem, given the actuator inputs, find the output displacement. So, where is the output? So, as I have mentioned this before, if I give this displacement, where is this link? If I give a displacement of this much, where is this wheel link? This is a forward kinematics problem. Similarly, in this parallel kinematic machine, if I specify, these are the actuators, if I specify this actuator through, this actuator through, and there is another actuator at the bottom, if I specify these 3 actuators, where is the end point, the end effector point? So, that is the forward kinematics problem. The second problem is that of the inverse problem. So, inverse kinematics problem, for a specified output displacement, find the actuator inputs. This is very relevant. If I want to position, for example, this chair to the standing position, I am specifying this position, what should be the throw of this actuator? That is the inverse kinematics problem. Or if I want to specify the location of the bin, at a certain position and orientation may be a certain position, let us say, what should be the actuator inputs? So, this is the inverse kinematics problem. Now, let us plan our study of displacement analysis. So, as I have planned, we will first discuss constraint mechanisms. You know that constraint mechanisms are mechanisms with 1 degree of freedom. So, we are going to study displacement analysis of constraint mechanism, we will start with that. Subsequently, we will go to robots. So, we will look at open chain robots and closed chain robots. So, today we will start with the analysis, displacement analysis, the forward kinematic analysis of a 4R chain. So, we are going to start with constraint mechanisms, and under constraint mechanisms we are going to discuss two kinematic chains, a 4R and a 3R1P. In this lecture we are going to discuss 4R chain, the forward kinematics of it. So, here I have shown a 4R chain. So, what is the problem? Let us see. So, the forward kinematics problem for a 4R chain is given theta 2, which is the input, which I call the input. So, given this, find theta 4, the output. So, this is the forward kinematics problem for the 4R chain. So, this is what we are going to study. Let me draw the coordinate system that I choose. So, theta 2 is, as is clear, I think theta 2 is this angle, theta 4 is this angle, and we can also have theta 3 as a byproduct of the calculation. But we are primarily interested in finding a relation between theta 2 and theta 4, that means given theta 2, what is theta 4. So, here I have marked 2 points P and Q, these are the 2 hinges. So, coordinates of point P in this coordinate system is L2 cos theta 2 and L2 sin theta 2. So, this is the x coordinate and this is the y coordinate of point P. Similarly, I can write coordinates of point Q. So, in order to write that, I must add this L1 along x. So, L1 plus L4 cos theta 4, which is so L1 plus L4 cos theta 4 is the x coordinate of point Q, and L4 sin theta 4 you can see from the figure is the y coordinate of point Q. So, therefore, this link length L3 can be expressed as L3 square is equals to, as you can see here, x q minus y q whole square, x q, sorry, this is x q minus x p whole square plus y q minus y p whole square, and that is L3 square. So, that I have written out. Now, if you open this up, then what do you have? So, L3 square is equals to L1 square plus, now L4 square cos square theta 4, and from here I will have L4 square sin square theta 4. So, it is L4 square. Similarly, L2 square cos square theta 2, L2 square sin square theta 2 will come in addition, therefore, this will become L2 square. Now, the cross terms 2 L1 L4 cos theta 4, which I will write as C theta 4 minus 2 L1 L2 cos theta 2. So, C theta 2 and minus 2 L2 L4 cos theta 4 cos theta 2, and one cross term from the second square. So, that will be minus 2 L2 L4 sin theta 4, S theta 4 is sin theta 4 and S theta 2 is sin theta 2. So, this is what we will get. Now, I can rearrange it like this: sin theta 4 times. So, let me see what are the sin theta 4 terms. So, here I have the sin theta 4 term, so this becomes 2 L2 L4 sin theta 2. Then I will look at the cos theta 4 terms. So, I have cos theta 4, this is one term, this is one term, that is it. So, I can write so this comes with, so this term I have taken to the left hand side, so that this I have written positive. So, I must take all terms to the left hand side. So, cos theta 4 2 L1, so this will come with a negative sign 2 L1 L4 and plus 2 L2 L4 cos theta 2 and that is equal to L1 square plus L4 square plus L2 square minus L3 square. I am bringing L3 square to the right hand side minus 2 L1 L2 cos theta 2. So, this is what I have. Now, if I do a little bit of simplification, then I can write it as A sin theta 4 plus B cos theta 4 is equal to C, where A, B, C are functions of theta 2, as you can see. So, let me formally show you this step. So, A sin theta 4 plus B cos theta 4 equal to C. I have done some simplifications. So, A is sin theta 2 and B has these expressions and C has this expression. So, what is our goal now? Goal is to solve this. Why? Because I am given theta 2. If I am given theta 2, I know A, I know B, I know C. They involve theta 2. I know them. What I have to find? I have to find out theta 4. So, I have to essentially solve this equation. So, I have to solve this equation to solve theta 4. Now, we are going to do it in a manner which can be computerized. So, in a computer, as you know, that these trigonometric functions will have two solutions, double solutions. So, we are going to devise an approach which will take care of this thing, and we are going to get both the solutions. So, how to do that? By the way, you can relate theta 3 as tangent theta 3. So, you can see this. This is theta 3. So, tangent of theta 3 is this distance divided by this distance, and this distance is yq minus yq minus yp by xq minus xp. That is tangent theta 3. So, theta 3 stands for tan theta 3, and you can just substitute these expressions and find that this is what it is. So, we can once I know theta 4, once I have solved for theta 4, because theta 2 is already known, once I have solved for theta 4 from here, I can substitute here and get theta 3. So, that is our plan. So, right now this is our plan, solving this equation in a manner which can be computerized. We want to get all the possible solutions. So, solution of A sin theta 4 plus B cos theta 4 equal to C. So, here we make a substitution, x is equal to tan theta 4 by 2. Now, how does that help? Now, tan theta 4 by 2 can be used to write sin theta 4 by 2 like this, which is a standard, because 2 times tangent of theta 4 by 2 by 1 plus tangent square theta 4 by 2, that is this expression on the right hand side, is equal to, now if I write tangent theta 4 by 2 as sin theta 4 by 2 and cosine theta 4 by divided by cosine theta 4 by 2, then you can very easily see that this is sin theta 4 by 2 divided by cosine theta 4 by 2 divided by, now here it becomes sin square theta 4 by 2 plus cos square theta 4 by 2, which is 1 divided by cos square theta 4 by 2, and that turns out to be 2 sin theta 4 by 2, and this goes to the numerator and cancels off with 1 cos theta 4 by 2. So, this only leaves 1 cos theta 4 by 2. So, 2 sin theta 4 by 2 into cos theta 4 by 2 is sin theta 4. In a similar manner, this cos theta 4 by 2. So, if I look at the right hand side, then 1 minus tan square theta 4 by 2 by 1 plus tan square theta 4 by 2. Now, again I write tan theta 4 by 2 as sin theta 4 by 2 divided by cos theta 4 by 2. So, in the numerator I have cos square theta 4 by 2 minus sin square theta 4 by 2 divided by cos square theta 4 by 2, and on the denominator I will also get 1 by cos square theta 4 by 2. So, this becomes 1. Now, cos square theta 4 by 2 minus sin square theta 4 by 2 is cos theta 4. So, we have looked at these two expressions. Now, if I substitute this in place of sin theta 4 by 2 this expression, and in place of cosine theta 4 by 2 this expression, then I get this equation, which I can simplify. This is a very easy step, I leave it to you to show that you get this quadratic equation in x. Remember, x is tangent theta 4 by 2, tan theta 4 by 2 is x. Now, you know that the quadratic equation has these are the roots of the quadratic equation. There are two roots of the quadratic equation which can express explicitly. So, this is what we are going to look at next. So, this was the quadratic equation that we obtained. So, solutions which is essentially tan theta 4 by 2. So, x is tan theta 4 by 2. So, you know this solution of quadratic equation, roots of a quadratic equation. So, you have it in this form, and you also remember that we have these a, b, c expressed previously. So, these are the definitions of a, b, c in terms of theta 2 and the other link lengths. So, I can find out x, and hence I can find out tan theta 4 by 2 in terms of theta 2. So, let us do that. So, tan theta 4 by 2 is this expression in terms of a, b, c. So, there are these two possible solutions, theta 4 1 and theta 4 2, theta 4 1 and theta 4 2, with here you have this plus minus. So, I have taken 1 by 1. So, here I have taken the minus, and here I have taken the root with the positive sign, and I do tan inverse. Now, this tan inverse is quite powerful. In most softwares, in programming languages, this tan inverse is given in terms of a function called a tan 2. So, once I have theta 4 and theta 4 1 and theta 4 2, I can solve for theta 3. So, for these two solutions, theta 4 1 and theta 4 2, I have two solutions of tan theta 3 or theta 3. Now, this tan inverse is to be, or the inversion of tan, for inversion of tan, to get the correct quadrant, of the angle, you need to use this function a tan 2. This is available in most programming languages and in softwares, numerical softwares, a tan 2, or sometimes also known as arc tan 2, and it gives, it has two arguments y and x. So, it calculates, so a tan 2 y comma x is actually nothing but tangent inverse, so tan inverse y divided by x. What it does extra? It looks at the sign of the numerator and the denominator and thereby decides, so sign of numerator and denominator. So, it looks at the sign of the numerator and denominator and thereby decides the quadrant. So, this is very powerful. So, it will tell you the correct quadrant of the angle. As you know that in the first quadrant everything is positive, in the second quadrant sign is positive, which means that the numerator if it is positive and the denominator if it is negative, then it must be in the second quadrant. In the third quadrant both sine and cosine, so are negative and therefore tangent is positive. So, if you have y also negative and x also negative, then it will give in the third quadrant, and if you have in the fourth quadrant cosine is positive and sine is negative. So, if it sees that the denominator is positive while the numerator is negative, so it will give the angle in the fourth quadrant. So, this function does all that automatically for you. So, you need not worry about the quadrant. So, you should explore this function a tan 2 y comma x. Let us look at the graphical picture, the geometric interpretation of the two solutions. Now, theta 2 is specified, as you know theta 2 is specified. We want to find out theta 4. Now, this hinge therefore can rotate because theta L4 is specified, L4 is fixed. So, this theta 4 can be any angle such that this hinge lies on this circle. Since this hinge is fixed because theta 2 is fixed, so this hinge is fixed. So, therefore, on the link L3 can rotate with this as the center on this circle. Now, these two circles have two intersections. This is one intersection, this is the other intersection. So, you can assemble the mechanism in this configuration, the black one or this red one. Now, whether these two are distinct assembly modes, that will be decided by whether this mechanism is a Grashof chain or not. But you can assemble the mechanism in two ways like this. So, these are the two solutions that we are obtaining. So, 4 has two solutions. So, this is one solution and this is the other solution. So, you can see that one is in the first quadrant, the other is in the third quadrant. So, this will be done automatically by the a tan 2 function. So, this is the graphical picture, this is how we can understand the solution. To summarize, we have looked at the displacement analysis of mechanisms in general and defined the forward and inverse kinematics problems, and here today we have looked at the forward kinematics of a 4R kinematic chain, a constrained kinematic chain. So, with that I will close this lecture.